Welcome back to another episode of Calculus of Variations for NoRmIeS, the only show where we maximize our time by minimizing functionals. In physics, this concept actually has a name, and it's the only physics idea which accurately describes my love life. It's usually known as the principle of least action. Alright, so we want to start as before with some integral which we want to minimize. This integral is known as the action s, and this function of x, its t derivative, and possibly also explicitly t, is known as the Lagrangian, or at least in physics it is. And what we want to do is, as before, consider that we already know for what function x this integral is going to be minimized. And of course, I is just going to be some subset of the real numbers, so that t is parameterized by I. Okay, so let's suppose that x is equal to u plus epsilon v, where epsilon is our new independent variable. We know that u, by supposition, minimizes this, and v is just some arbitrary function which we're going to pose some boundary conditions on later. Alright, so now we can think of this as s is equal to integral over I of L of u plus epsilon v. What is x dot going to be? Epsilon is independent from t, so this is going to be u dot plus epsilon v dot, and t, of course, dt. Alright, so now we want to take a derivative with respect to epsilon and then set it equal to 0, so that we can find the minimum or maximum or any stationary value, critical point, if you like. So, ds d epsilon is going to be equal to, we're going to bring the epsilon derivative inside the integral, in which case it becomes a partial derivative of the Lagrangian of u plus epsilon v, u dot plus epsilon v dot, t dt is going to be equal to integral over I of, so we're going to want to use the chain rule here, so it's going to be dl dx times dx d epsilon plus dl dx dot times dx dot d epsilon plus dl dt times dt d epsilon dt, where we're going to set x is equal to u plus epsilon v later. So the first thing we should notice is that epsilon and t are independent from each other, so this is just going to be equal to 0. And derivative of x with respect to epsilon is just going to be v. This is going to be v. And derivative of x dot with respect to epsilon is just going to be v dot. This is equal to integral over the interval I of dl dx times v dot, or sorry, v plus dl dx dot times v dot dt. Alright, so I rewrote our basic information over here, so let's continue. We're going to keep this half the same and then integrate this half by parts. First integrating v dot with respect to t, so this is going to be equal to integral over I of dl dx times v dt, and then the by parts part is going to be plus, and we're going to have dl dx dot v evaluated at on the boundary of I minus the integral over I of the time derivative or t derivative of dl dx dot times v dt. Okay, so now we're going to impose a stipulation, which is that this arbitrary function which we're adding a multiple of epsilon times that to our minimizing function u, we're going to, likewise, just as with the Dirichlet principle, we're going to allow ourselves to set it equal to 0 on the boundary and allow it to move however we want within that, so that u satisfies whatever prescribed boundary conditions we want. The v isn't contributing anything there. So this is going to be equal to 0. And we can combine these two integrals to get integral over I of dl dx times v minus the time derivative of dl dx dot times v dt. Now what's interesting here is that we have v, our arbitrary function, in both terms, so we can actually factor that out. So let's write this as integral over I of dl dx minus ddt of dl dx dot, and then write v over here. Okay, so now we have it written in its final form here, where this is our derivative with respect to epsilon of the action, and we of course want this to vanish in order for us to get a critical point, or minimum or maximum, whatever it turns out to be. So this must equal 0. When we set epsilon equal to 0, then we're also going to lose the v component, but v can still be whatever we want so long as it is 0 on the boundary. But since this has to vanish for any possible v in between there, this is going to imply that whatever's multiplying v has to be 0. And thus, we get the derivative of the Lagrangian with respect to x minus the time derivative of the partial derivative of the Lagrangian with respect to x dot must equal 0. This is our Euler-Lagrange equation. It is a differential equation that will give us, at least physically, an equation of motion corresponding to the coordinate, or generalized coordinate, x. So, just by assuming that this action has some critical points, which are functions x of t, so functions x of t which maximize, minimize, or perhaps there's an inflection point, they have to satisfy then this additional differential equation which we can solve, at least in principle. Alright, now how does physics use this? Well, in physics the Lagrangian is defined as the kinetic energy minus the potential energy of a system. So if you can figure out what this is, and then any additional constraints, you can obtain the equations of motion and the constraints that they have to satisfy, and thus solve the system, at least in principle. Alright, let's just look at a pendulum here to see how the equations of motion can be derived. So what we need to know is the potential energy of the system and the kinetic energy of the system. So the potential energy for this system is just going to be gravitational potential energy, and it's going to have the form negative mgl cosine of theta. Not going to spend much time talking about where that comes from, but you can think of, if you wanted to derive it, projecting this onto this sort of axis and then looking at the regular mg times the height for your gravitational potential. Okay, so that's going to be our potential energy. All right, so that's the potential energy. Now what about the kinetic energy? Well, it's going to be equal to 1/2 mv squared, or 1/2 mx dot squared, but of course we're not moving in a straight path. We're going to be going in circular motion, so that the angular velocity is what we're interested in, and these are going to be related in the way x dot is going to be equal to theta dot times the radius, which is L here. So that this becomes 1/2 m L squared theta dot squared. Alright, so we have 1/2 ml squared theta dot squared is equal to t. Now we can form our Lagrangian and figure out the equation of motion that's going on here. And notice that our constraint is already built in the way I've set this up, which is that we have a fixed radius, right? This is a rigid, massless rod. Okay, so Lagrangian is equal to t minus v is equal to 1/2 ml squared theta dot squared minus minus is going to be plus mgl cosine theta. So that we're going to have the derivative with respect to, and we're going to go theta, this is our generalized coordinate here, is going to be equal to negative mgl sine theta, right? And we're going to have the derivative with respect to theta dot is going to be equal to, this is going to be ml squared theta dot. So that what you're going to get, if you take the time derivative of that, it's going to just pass through those constants, and this is going to be a double dot. So that if we set them equal to each other, as in the Euler-Lagrange equation, we're going to have ml squared theta double dot is equal to negative mgl sine of theta, and we can divide by ml squared and then move this term over, and we'll get theta double dot plus, and we're going to have plus g over L sine theta is equal to 0. And this is, of course, our differential equation for the simple, well, not necessarily the simple, but the pendulum, the single pendulum. If we want to do the simple pendulum, we look at the Taylor series of sine theta and theta and make a low-order approximation for small angle oscillations, right? So this is just an example of how constructing this Lagrangian from the energies and then using this Euler-Lagrange equation gives you your motion equations without necessarily introducing vectors. So that's pretty cool. So this remarkable idea that you can find the stationary values, or critical points if you like, of the action, and that those are going to yield the actual trajectories for your system, is known as the principle of stationary action, or principle of least action if you like, but it's not always a minimum. So there you have it, Euler-Lagrange equation and principle of stationary action. Hope you enjoyed this episode of Calculus of Variations for NoRmIeS, and I'm excited to see you again next time.